All right, guys, this is Ms. Hodges here. I'm here to talk about friction, this worksheet in particular. We're going to work through the problems together. Again, if you haven't started working on the worksheet already, or if you haven't attempted to work on it, I would encourage you to attempt to do it. It's not helpful to you at all if you just get the answers, but you don't attempt to do it. Because obviously the test will not be something that I'll be able to assist you on. So help, this is just supposed to be a supplement. So let's get started. All right, so we're going to start off at number one. Well, first of all, let us highlight a couple of equations that we have available to us. And these equations we're going to use for all of these problems that we have. So it's going to be really important that you know what these equations are so that you know how to use them and when to use them. Right? So our first equation here is our velocity equation. Velocity equals distance over, or displacement over time. Our next is the acceleration equation. Our acceleration is equal to the the final velocity minus the initial velocity over time. Next is our distance equation. We can determine the distance that an object has traveled based by multiplying 1/2 of the acceleration times the time square. Next is is a constant. So just so that we know that this one is a constant, I'm going to highlight it in green. It's a constant, not an equation. It's a constant that lets us know that whenever we have to use gravity as acceleration, our acceleration, that is always going to be negative 9.8 meters per second square. And don't forget that number is negative because anything that is under the influence of gravity is being pulled downward, and that downward direction is a negative direction. Lastly, is our F. Our force, our net force is equal to mass times acceleration, right? The mass of an object times the acceleration that it's undergoing. So let's go ahead and start with number one. Number one says, let me get the right color here. I'll go with red. Number one says you are pushing a cart that weighs 5,400 newtons, right? So first we're going to annotate our question here. So we're pushing a cart. So there's an applied force. That applied force is going in a direction, in a particular direction, and we're pushing it with 5,400 newtons of force. The frictional force is 43 newtons. Okay. So we're going to draw a force diagram and label force of gravity, the normal force, force of friction, and the applied force. So a force diagram really is a diagram that helps us understand the direction of the forces that that are being applied to an object, right? And if we do, we're gonna draw a nice little square here. And this square is going to represent an object. And this is our object. So we're going to apply some different forces, okay? So let's say we're pushing an object. That means the object has an applied force going in a direction. So if I'm pushing an object, I'm going to say that I'm pushing the object to the right. Okay, I'm pushing the object to the right. So there's an applied force here. And the force is applied because, again, we're applying the force. We are pushing it. And that force is equal to 5,400 newtons. Okay. Now, obviously, if we're pushing an object, then that's an applied force. The force that opposes an applied force is frictional force. And if it opposes an applied force, it's going to go in the opposite direction, right? And so if this is our opposite direction of our applied force, this is going to be our force of, and it's going to be a big F sub little f. If I can get it. There we go, F. All right, and that force of friction that's applied, that is a force in the opposite direction, is equal to 43 newtons. 43 newtons. Okay. Gravitational force is always going to pull an object down, so we know that that object is going to go in the downward direction. This is our force of gravity. And then the force that our normal force, our supportive force, is if it's sitting on a table, that table or the floor, that force is applied in the upward direction, opposing gravity. And so that's our normal force, and it's going to go opposite of our gravitational force. And so that's our force, our normal force. And that is our force diagram. All right, so part B says, how hard do you have to push in order to move the cart at a constant velocity? Now, this is a pretty tricky question because it's not asking us how hard do we have to push to make the box move, but how hard do we have to push to keep the box moving at a constant velocity, right? So that is where if I have a constant velocity, then I know that it's not speeding up and it's not slowing down. All right, it's not speeding up, it's not slowing down because the speed is the same. So if the speed is the same and I'm not increasing and decreasing in speed, that means that I don't have an acceleration. Okay, let's think about this for a second. If my net force is equal to my mass times my acceleration, and because my velocity is constant, I don't have an acceleration. My velocity is constant, I don't have an acceleration. So essentially my acceleration has become zero. Well, m times zero, or anything times zero, is going to equal zero. So I have a net force, F net, equal to zero. So that means that I have to push the box in with enough force that my net force will equal zero. So I know that if I have my box here, and I know the force of friction in one direction is 43 newtons, how hard would I have to push the box in the opposite direction in order for my net force to equal zero? Well, basically, that just means my force has to cancel out. So that means I have to have a net force in the opposite direction of the same force as my frictional force. So that means 43 newtons in my applied force in that direction. So that I know that my applied force, my F applied, would have to equal 43 newtons. All right. So let's go to number 2. I'm going to zoom in here so we can write this. Makes sense. All right, so you exert a 0.98 Newton rightward force on a 2.3 kilogram cart. Okay, so if you exert a 0.98 Newton rightward force on a 2.43 kilogram cart, what should the acceleration be of the cart be? All right, so I know that I'm dealing with forces and I'm dealing with acceleration according to this equation. Dealing with forces here, dealing with acceleration. So what is it that I know already? Well, I know that I have an applied force. I know that I have an applied force of 0.98 newtons. I know that I have a mass right here of, let's see, 2.43 kilograms. And it's asking me, what should my acceleration be? I'm looking for my acceleration. What should the acceleration be? So I'm looking for acceleration. Now, not to do some Dora the Explorer type of stuff, but if I'm given a force, I'm given a mass, and I'm looking for an acceleration, which of these equations up here at the top would I use in order to find acceleration? It would have to be an equation that has both an F, an M, and an A. And if you said that it's F net, if you chose F net equals MA, you would be right. I need to use my force my net force equation. So I know that F net equals mass times acceleration. So I have an F, I have an M, and I'm looking for an A. So that's how I know I got the right equation. So let's go ahead and solve it. All right, my net force is 0.98 is equal to my mass is 2.43 kilograms, and I'm looking for the acceleration. And I'll just do some simple calculation here. Let's divide 2.43 by both sides, 2.43 and 2.43. Divide that by both sides. It's 0.98 divided by 2.43, and that gives me 0.4, so that my A is equal to 0.40, and it's an acceleration, and I never ever 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 forget my units. Acceleration's units is mass per meters per second squared, and that is my answer. All right, now I have my answer for number 2. Let's go to 2B. The cart has a measured acceleration. So theoretically speaking, my acceleration should be 0.4 meters per second squared. But of course, in real life, they don't always equal up to our theoretical measurements. And so they actually measure the acceleration at 0.22 meters per second. What is the frictional force? So this one's going to get a little bit more involved, and that's okay, because we know that when we have certain amount of information, we can figure out the rest of our information. Okay, so we can go about this in a couple of ways, and I think I'll go about it the pretty simple way. So I can say that I have a box, right? And I think this is the best way to start off. I think I'll start off with a force diagram. And if you're unable to figure out how to get it started, just do a force diagram. It will never hurt you to do one. It's always helpful to use one so that you know you have the right answer, so you know what you should be looking for. Okay, so we exert a rightward force on a cart, and the force that we exert is 0.98 newtons, and we know that we have a frictional force in the opposite direction of some amount. Okay, so I need to pause it for a second. I have a student. All right, sorry about that. So what I'm trying to find out is the frictional force. So theoretically speaking, I have a force I am pushing with a force of 9.8 newtons, 0.98 newtons in one direction, and that means I should be traveling with an acceleration of 0.40. But the reality is I'm only traveling with an acceleration of 0.22 meters per second square, and that is because frictional force is slowing me down. So again, there's a couple of ways I can go about doing this, and I think that the easiest way is to determine our frictional force in the opposite direction by figuring out what is the difference between our accelerations and multiplying that by the mass. The reason why I don't particularly like this method is because it doesn't really explain why you have this difference in frictional force, but it's the easiest way for us to be able to explain it, and maybe I'll go back at the end of this video and go back and re-explain it a different way. But if I have an actual measured acceleration of 0.22 and a theoretical acceleration of 0.40, then I'm going to find the difference between those two accelerations. The difference between those two accelerations should be the acceleration in the opposite direction, And so what we'll do is we'll say that we have a theoretical acceleration of 0.40. And we're going to subtract that from our actual measured acceleration of 0.22. And that should give us a acceleration equal to 0.18. And that's meters per second squared. Now, if we multiply this 0.18 times the mass, so we have our force of friction. That means if we multiply our mass, and that's 2.43 times 0.18, that should give us our frictional force, our force of friction in the opposite direction. So I'm going to do that really quick. 0.04, I'm sorry, 0.40. Oh, that's still not the right one. 2.43 times 0.18. And that gives me a force in the opposite direction, so that my F, my frictional force, is 4.437, so I'll say 0.44. That means my frictional force in the opposite direction is 0.44 newtons. Again, it's a force. We measure force in newtons, so 0.44. Last question. A falling skydiver, and so we already know that our object is in the air because it's falling, is accelerating in the downward direction at 3.29 meters per second. The mass of the skydiver, including the parachute gear, is 67.2 kilograms. Determine the air resistance force on the skydiver. All right. So again, this problem is similar to the one above, and so we're gonna go ahead and annotate this question so we know what we're looking for. So we know we have a falling skydiver is accelerating in the downward direction at 3.29 meters per second squared. That's our acceleration. The mass of the skydiver is 67.2. That's our mass. And we want to determine air resistance. Air resistance is a form of friction, force, frictional force, and it's our force of air resistance. It opposes gravitational force, right? So if our object, and I'm gonna erase this one and make it a little bit bigger so that we can see what's happening here a little bit better. There we go, nice big box, big skydiver box. He is falling, and this gravitational force is pulling him down. This is our force of gravity. We have another force acting opposing that gravitational force in the opposite direction. This is our force of air resistance. We know that our box is 67.2 kilograms. And so I need to know, what is the force of air resistance? It seems like we don't have enough information, but I can guarantee you we have all the information we need. To find our net force, we need to find, if we want to find our F net, we need to find the sum of all of our forces, right? It's the sum of all of our forces, and sum of our forces. And if we want to find our sum of our forces, we need to find what each force is. So how do we go about doing that? Well, we can find our force of gravity because we've been given the acceleration in the downward direction and the mass. So let's go ahead and find our our force of gravity, our actual measured force of gravity. So F of G is equal to the mass, which is 67.62. I'm sorry, 67.2 times, and again, there's a couple ways to do this. It's similar to the second, to the B, part B of number 2. We're just doing it in a little different way. Our F of gravity is our mass times our acceleration. Our acceleration, according to this problem, is 3.29. So we're going to put 3.29. And that's our measured acceleration. We can find force of gravity once we multiply those, and we will. But here's the problem. The problem is that if an object is in free fall and is falling, it should not be falling with an acceleration of 3.29, should it? The acceleration of gravity, right? So we can say the acceleration of gravity, according to this problem, according to this, what do they call it? Constant is not negative 9.8 meters per second squared. So that means that our acceleration is less, our actual measured acceleration is less than what our gravitational constant should be. So if we can find the difference between the two of those, then we know that we can find the force of air resistance. So our real force of gravity should be 67.2 times, and we're going to say 9.8 meters per second squared because I'm looking for the absolute value. I'm looking for the magnitude, and I know what the direction is, which is why I don't necessarily need the negative here. So 9.8. That's what the force of gravity, the force due to gravity should be. And if I can find the difference between these two, then I have found my force of air resistance. So let's do it really quick. 67.2 times 3.29 equals 221.8. That's my force, gravity. So that's 221.01. And then I'll just do the same thing down here. 67.2 times 9.8. 9.8. Let me try that one more time. I think I might have made a calculation error. Times 9.8. There we go. 658 point, let's say 56. Can round it to the nearest whole number. And what I need to do is just find the difference between these two numbers, and the difference between these two numbers, if I subtract the force of air resistance, is the difference between theoretically what my force of gravity should be and my actual force of gravity is. The force of air resistance is equal to 437.55 newtons. And that's how you solve that problem. Now I would go back up and resolve this one in a different way, this problem here. But either way of solving those problems is correct. You can either find the difference in the acceleration, or you can find the difference in the theoretical versus the actual forces that we measured. In fact, if you really want to know how a quick way to do it, if you're given this problem again, I'll work it out really quick, and I'll just work it out as I write. I'll erase it over here. And if you can follow along, that's great. So I know that my mass is 67.2 kilograms. I know that the actual, my theoretical acceleration of gravity is 9.8 meters per second square, and I know that the measured acceleration is 3.29, And let's find the difference between those two numbers. It's 9.8 minus 3.29, 6.51, 6.51 meters per second squared. All right, and that's my acceleration. So that's difference in acceleration. I'm going to multiply, I'm going to say that my F of air is equal to that acceleration times the mass of my parachute diver. So that's 67.2 times 6.51. And I should get 437.55 if my calculations are correct. 67.2 times 6.51. And that's exactly what I get. That's 437.5 newtons. Again, either way one of those works, those both work the same way. All right, hopefully that helps you understand the problems a little bit better. If you have any questions, then I'll have my email up in the link down below. And if you need to contact me, I would encourage you to just email me. I will definitely try to get back to you as soon as I can. All right, guys, have a good one.